Hello and welcome back. In today's lecture, which is number 2 of 2 for chapter 7, I'd like to discuss kinetic energy. Now, if you remember our lecture last time, one of the things that I'd mentioned was that when you do positive work, you cause an object's speed to increase. And if you do negative work, you cause it to decrease. So clearly, there is a relationship between work and changes in speed, changes in motion. Kinetic energy is energy in motion. Okay. And if you remember our conversation about trying to define energy in a more reasonable manner and how they had gone back and looked at what Aristotle had originally done, I mentioned that an object's ultimate purpose is to experience a change in motion. And the things that can potentially cause that change to occur would be forces. So, to explore kinetic energy, what I'd like to do is to start with the definition of work, specifically incremental work or differential work. Now, we'd worked extensively with this last time, and it looks like this. Okay. Now, so that said, I'd like you to also recall that according to Newton's second law, you can write force as an object's change in momentum over time. Now, remember, assuming you have a constant mass, this is the same thing as m dv dt or m times a. Likewise, velocity we know you can write as an object's change in position over time. So what I'd like to do is to rewrite our differential work here as being m dv dt times, if I rewrite dr as v dt, Now, there's a dt on the top and a dt on the bottom. They cancel each other out. And if you use the fact that, a dot b is the same thing as b dot a, you can rewrite this as dw, or d work, is mv dot dv. Now, dv looks a lot like dr. It would be your change in velocity in the x direction plus your change in velocity in the y direction plus your change in velocity in the z direction. Okay. Now v, remember, we can write as vx x hat plus vy y hat plus vz z hat. So if you're to actually carry out this dot product, this is what you would be doing. You would multiply by component them against each other. So it would look something like dx, whoops, sorry about that, vx vx plus vy dvy plus vz dvz. Okay, this is what dw would look like. Now, what I'd like to point out is this stuff on the right-hand side really only depends upon your velocity. Okay, specifically in this case, your speed, because dot products give you numbers. They don't give you vectors. And like I had hinted about earlier, work causes a change in speed. Now, to get there, what I'm going to do is to integrate both sides. So if I integrate the left-hand side, from where my velocity starts to where it ends, here I'm going to integrate the right-hand side. But when I do, I have to integrate over x, I have to integrate over y, and I have to integrate over z. I would end up with three integrals that look like this. we'll say from our initial x velocity, let me be consistent with my notation here, my initial x velocity to my final x velocity of m vx dvx plus m times my initial y velocity to my final y velocity vy dvy plus m, again, initial z velocity to final z velocity. And let's take a look at these integrals right here. Now, if you remember last time, we had used an integration rule that looked like this. If you integrate, you will say from a to b, x dx, that's the same thing, or x to the n rather, dx, that's the same thing as 1 over n plus 1, x to the n plus 1, evaluated from a to b, right? So really, that's the same thing that you have here. So instead of it being x, you would have vx or vy or vz. So really, when you look at the left or the right-hand side, the left-hand side is just the work. When you look at the right-hand side and you integrate these things, this, for example, would become 1/2 vx squared, evaluated from initial to final. Okay, this right here would be 1/2 vy squared. This right here would be 1/2 vz squared. Okay, so that's what your integrands would look like whenever you're done with them. So what that means is your first term right here would look like 1/2 m vx squared, evaluated from v naught x to vx. The second term right here is going to look like 1/2 m vy squared, evaluated from v naught y to vy. And our last one here is going to look like 1/2 m vz squared, evaluated from v naught z to vz. Now, we know when we take and we plug this stuff in, you end up with something that looks like 1/2 m vx squared minus v naught x squared plus 1/2 m vy squared minus v naught y squared plus 1/2 m vz squared minus v naught z squared. Okay, so that's left hand work, right hand all this stuff right here. Now, so check this out, right? So what if I took and I looked at v dot v? Okay, now if I did this, this is the same thing as asking what is the magnitude of v squared. All right. Now let me remind you about the Pythagorean theorem. Remember, opposite adjacent hypotenuse. This right here we'll call C. This we'll call A. We'll call B. And we know that C squared is equal to A squared plus B squared, right? So look at this. This is the same thing as, we'll say, C squared. You have, when you do the piece by piece dot product like we did up here, vx squared plus vy squared plus vz squared. Okay, so this is really the same thing as v squared, if you want to think of it like that. And if you take a look here, what we have is vx squared plus vy squared plus vz squared. This right here is v naught squared. You have v naught x squared plus v naught y squared plus v naught z squared. You just happen to be subtracting v naught squared away from the whole thing. So what that means is that I can write this the following way. If I group up all the terms together, all the terms that belong with v itself, vx squared plus vy squared plus vz squared, and call that v squared, and do the same thing for v naught, I get 1/2 m v naught squared, or v naught, please, v squared minus v naught squared. Okay, now let me go ahead and multiply that 1/2 m through. 1/2 mv squared minus 1/2 mv naught squared. Now look, this is a final, this is initial. When you take and you subtract the final minus the initial, like this, when you do this, this gives you a change in it. Okay, so here I'm doing work on something and I'm clearly causing a change in something. Well, we kind of talked about what was changing, right? Because when you do positive work, don't you cause the speed to increase? When you do negative work, you cause it to decrease. So what you're doing is you're increasing the energy that's in motion, or you're decreasing the energy in motion. You're causing a change in it. So this change right here, is the change of your motion energy. Now, we call it kinetic energy. We use the letter K for it. K actually is defined as 1/2 mv squared. That's what we call it right there. Okay, this is kinetic energy. That's what this is. And this right here, this relationship between work and changes in kinetic energy, is actually a very important equation. It's called the work energy theorem. Okay, so when you do work on something, what you do is you cause it to experience a change in kinetic energy. If you do negative work, the change is negative, and you can see why here. So if you do negative work on something, what that means is that what you're subtracting here is bigger than what you're subtracting from. That means this number is bigger than this number. Your final kinetic energy is bigger than your initial kinetic energy, which means that, assuming your mass is constant, which is what we typically assume in situations like this, your initial velocity is greater than your final velocity. You've slowed down. When you do positive work, what that means is that your final kinetic energy is greater than your initial. So the difference between the two is positive. Okay? So very important thing, work energy theorem. Something that you should put in your notes and put a huge star beside, because you never stop saying it. So that said, let's just do some simple calculations here, dealing with kinetic energy, so we can get a feel for how it works. First of all, what is the kinetic energy of a 0.25 kilogram baseball that's been pitched at 50 miles per hour? So what we're given here is a mass of 0.25 kilograms and a velocity or speed of 50 miles per hour. Now, you'll notice I'm using speed and velocity interchangeably. You really can't, but in a situation where you're dealing with kinetic energy, what I'd like to point out is that you're dealing with the magnitude. Okay, now we know the magnitude of your instantaneous velocity is your instantaneous speed, which is typically what we're dealing with here. So anyway, we want to find the kinetic energy of this thing. This is very simple. So we just need to convert this to miles per hour. And if you do a quick conversion of it, let's see here. Let's see, 50 miles per hour is about 22 meters per second. So that would be about 22.4 meters per second. So just here, your kinetic energy is 1/2 mv squared, or 1/2 times 0.25 kilograms times 22.4 meters per second. squared. Now, this is incidentally one of the most common mistakes that I see made is forgetting to square that speed there. So make sure you don't forget to do that. So 0.5 times 0.2, or 5 times 0.25, whoops, times 22.4 squared about. So this ends up being about 63 joules. Now you might look at this and say, is this really a joule? Well, check this out. So you have a kilogram here. You have a meters squared over seconds squared. Now we know acceleration is meters per second squared. So if I pulled one of these meters out, I'd have kilograms times meters per second squared, which is a Newton. A Newton times a meter is a joule. Okay, so it is a joule. Okay, let's look at another example. What's the kinetic energy of a bullet that has a mass of 25 grams? I don't use G when I write out grams, I use GM. The reason why I use GM is because we've already used G for the acceleration due to gravity. Okay, so it travels at 340 meters per second. So again, what are we given? The mass is 25 grams, which is the same thing as 0.025 kilograms. But our speed is 340 meters per second. So we want to find K. So K is 1/2 mv squared, 1/2 0.025 kilograms times 340 meters per second squared. 0.025 times 340 squared. I get 1,445 joules, or when you round to 2 sig figs, about 1,400 joules. So that bullet actually has a substantial amount of kinetic energy if you compare it, say, to this baseball, right? Now, continue along. Let's take a look at a direct application of the work energy theorem. You've got a crate that has a mass of 34 kilograms. It's initially at rest, and here's as shown. Here's our coordinate system. Here's our crate. And we're going to push it like this, with a force like that. So our force is 120 newtons along the x-hat direction. We're going to start here at the origin, and we're going to push it until we get to about here. This right here would be x is equal to 1.5 meters. Now we're starting from rest, so our initial velocity is 0. And the mass of our crate here is 35 kilograms. Okay, now let's talk forces. Obviously, we have this force that's to the side. We also have the weight of the crate. We have the normal force, as a consequence of the crate pushing on the ground. So here's your normal force. Here's your weight. And I'd also like to point out that this is the direction of delta R. Why not dr? Well, we're dealing with a constant force. Okay, so we know what the equation for work is going to look like here. So let's draw our coordinate system over here for a force diagram. Again, only 3 forces, one of which is relevant. We have that, you have that, you have that, like that. So here's y and here's x. Here's our normal force. Here's our weight. And then here is the force of our push right there. Now, the normal force and the weight are going to cancel each other out, and as a consequence, they don't do any work. The force of our push, this thing is what's doing work. Okay. So what are we given? We're given that our force is 120 newtons x hat, the magnitude of which I'm going to call F sub x, as we've done in the past. The mass that we're dealing with here is 35 kilograms. Our initial velocity is 0. Our initial position is 0, 2. Our final position is 1.5 meters. And let's see, I think that's it. Yeah, that's all we have. What are we trying to find? The final speed of the crate. We're trying to find basically V. So what we're interested in using here is the work energy theorem. So when you do work, you cause changes in kinetic energy. And that change in kinetic energy is K minus K naught. But look, remember, K looks like 1/2 mv squared. So if your initial velocity is 0, your initial kinetic energy is going to be 0 because, it has this form. So that goes away. So really, your work is going to give us our final velocity here, our final speed. Okay. Now, we also know constant forces. Your work looks like F dotted with delta R. Now here, delta R is strictly along the x direction. Okay, it's going to look like delta x, x hat. So when I do this dot product, this is really just F sub x times delta x, which is what we've experienced in the past, since they're parallel to each other. Okay, so this is our work, and this is going to cause a change in kinetic energy. Okay, and our change in kinetic energy is going to look like 1/2 mv squared because our initial kinetic energy is 0. So if we want to find V, all we have to do is solve for it. Okay, it's going to be 2 F sub x times delta x over m raised to the 1/2 power, it's the square root. So if I were to plug stuff in here, F sub x is 120 newtons. Our displacement, final mass initial, ends up being 1.5 meters. And our mass here is 35 kilograms. So if I actually do the math here, so 120 times 1.5 divided by 35, I get 3.2 meters per second. Now, this is a speed, and that's one of the things that you need to be aware of when you deal with energy in general. Energy gives you a number, it gives you a scalar, and it's up to you to figure out the direction. Okay. Now, thankfully, here we're just being asked what the speed of the crate is, so we don't have to worry about that. But, in a situation where you're actually looking for the velocity, you would have to use common sense to figure out what that is. Here's another one. Now, this is more complicated because you're dealing with a force that's not constant. You have a 0.45 kilogram mass that's attached to a spring that has a spring constant of 30 newtons per meter. The spring is stretched 1.2 meters from equilibrium and then is released from rest. How fast is the mass traveling when it crosses the equilibrium position? I'd also like to know how far the spring is going to compress. Okay, now, so I'd like to like you guys to remember that we had gotten a result looking at the work due to a spring. Let me get rid of that. And it looked like minus 1/2 k times x squared minus x naught squared. Now, so if you think about what this is going to look like. So here's your wall. Here's the floor. Here's your spring. Your spring has a mass of 0.45 kilograms. There's a spring constant here of 30.0 newtons per meter. This we're going to call the zero. This is going to be our equilibrium position. So really our coordinate system is going to be, and I'll dot the y-axis here for us so it doesn't, get us confused with, with where the wall is. So this is where the y part of our coordinate system is going to be. And this is x. Okay. So we're releasing from here. This right here would be x is equal to 1.2 meters, like that. We also know that when we release, our initial velocity is 0, right? So what's going to happen is we're going to start this thing from rest. It's going to go zinging to the left, and when it hits the equilibrium position, it's going to have some, some initial or some final velocity rather. But we expect positive work to be done, right? Because you're going to be increasing the motion. So that work we expect to cause an accompanying change in kinetic energy. Now, that said, let's just go ahead and write out our givens and what we're trying to find. Given initial velocity is 0, spring constant is 30.0 newtons per meter. Our initial position is 0. Our final position, our initial position is 1.2. Sorry about that. Oh, why I did that. There. Final position. It's a day. There we go. Let me correct that here too. Our final position is 0. Our initial position is 1.2 meters. Our mass is 0.45 kilograms. And I think that's about it. We're trying to find two things. So the first thing we're trying to find is when it gets to the equilibrium, what's its speed going to look like? Okay. So we want to find V at x is equal to 0. But once it crosses the equilibrium position, what it's going to do is it's going to compress the spring. And the spring is going to act on it to slow it down. It's going to slow it down to the point where it comes to rest, and then it's going to push it back to the equilibrium position. So we're going to find, I'm going to call it x sub c, how far the spring has been compressed. Okay. So really what we have is two parts. We have one part here where the mass is moving this way. This is going to be the direction of, the force, but this is also the direction of dr. And then once it crosses the center line here, once it crosses the equilibrium position, what happens is dr is this way. It's still trying to compress it, but the force is trying to push it back to equilibrium, and that's as a consequence of slowing it down. So really it's two parts. So the givens that we have here really are for the first part. And what we're going to do is we'll work the first part, and then given the velocity that we find, or the speed rather, that we find at the equilibrium position, we'll use that as the initial velocity, and the final velocity will be when it's completely compressed, which will be when it's 0. Okay, so let's work the first part. So for the first part, our initial velocity is 0. So since work causes changes in kinetic energy, initial velocity is 0, kinetic energy initially is 0. So really what's happening is the work here that the spring is engaged in is just giving you your final kinetic energy at the equilibrium position. Now we also know that if you look at the equation for work, which is 1/2, k x squared minus x naught squared, that our final position for the first part, so I'm just going to put a 1 here, for the first part is 0. So our final position is going to be 0. A negative times a negative is a positive, which means that this is a 1/2 k times x naught squared. So on the left-hand side, you have kinetic energy. Kinetic energy looks like 1/2 mv squared. On the right-hand side, you have the work done by the spring to get it to there, which is this right here. And the negatives or the halves cancel. And if you solve for v, which is the speed of this thing at the equilibrium position, it's going to be the square root of k over m times x naught squared, or not x naught squared rather, but x naught. So remember, this is just a number. This is going to be, it should give you, when you calculate your v, a positive number. So our spring constant is 30.0 newtons per meter. The mass of our thing here is 0.45 kilograms. And we're starting at 1.2 meters, which means if you do this, let's see, 30 divided by 0.45, square root of that, times 1.2. I get 9.7979 meters per second. Keeping to the sig figs we have, which is 2, this would be about 9.8 meters per second. Okay. So now for the second part, we have different givens. Really, for the second part, the only thing that's changed is that our initial velocity now is 9.8 meters per second, and our final velocity is going to be 0. We also have an initial position of 0 since we're starting at the equilibrium position. Remember, it takes us to the equilibrium position and then it compresses it. So our initial position is 0. We're trying to find the compressed distance, basically, which is x sub c, which is what we'll put there in a second. We have our mass, which is 0.45 kilograms. And we have our spring constant, which hasn't changed, 30.0 newtons per meter. So what we're trying to find here really is x sub c. This is the compressed length. Or not really the compressed length, but the distance that's been compressed, rather. So just like before, work causes a change in kinetic energy. Here we know the work's going to be negative because it's slowing it down. And our change in kinetic energy is k minus k naught. Now here's the deal, though. When it's compressed, when it gets to this compressed spot, your speed goes down to 0. So that means our final kinetic energy is 0, right? So negative work, you can see. Your work here, once again, looks like minus 1/2 k x squared minus x naught squared. And as I'd mentioned before, we're starting at the equilibrium position in this one. So the negatives here are going to cancel each other out, which means that you have 1/2 m v naught squared on the left-hand side. And on the right-hand side, you have a 1/2 k x squared. So this is our compressed point right here. I'm going to call it x sub c. And if you solve for it, x sub c is equal to the square root of m over k times v naught. What's the square root of m over k? Well, m is 0.45 kilograms. K is 30.0 newtons per meter. And all this times v naught. V naught is that 9.8 meters per second. So when you do this, Let's see here. Oh, that's interesting. You get 1.2. So its compressed position would actually, since it's to the left, here, it would be negative. Like that. So our speed when it crosses the equilibrium position is this, and the compressed distance is the same as the distance as you released from. Well, that's interesting. See, what this suggests is that if it were to then push it back to equilibrium position, when it crossed the equilibrium position, it would be traveling at about 9.8 meters per second. And then it would slow down and stop 1.2 meters to the right. And then it would be pulled towards the equilibrium position, traveling at 9.8 meters per second whenever it crossed it. And that would compress to minus 1.2. And it would oscillate back and forth around the equilibrium position. And that's exactly what would happen. In fact, that type of oscillatory motion, that was the first clock. The first clocks were spring clocks. Now, let's see here. Let me scroll down a touch. Okay, now, so here's another spring problem. This one's different than the previous one because not only does this one include the spring force, but it also includes gravity. Now, thankfully, because of the way work works, you can find the work done by gravity, and the work done by the spring, and literally just add them together to find out what the total work is. But before we get to that point, let's draw a picture. So here we have a mass that's hanging from a ceiling. Okay, so this is the ceiling. This isn't the x-axis or anything like that. Now, what I'm going to do to sort of reference the axes here is to use dotted lines. All right. So if you read the text of the problem, we have a mass that's hung from the ceiling on a spring with a spring constant of 25.0 newtons per meter. What's happened here is that the spring has the mass hanging off of it. Whoops. And gravity is pulling it down more. It's pulling it past the equilibrium position. So if I think of this as my spring right here that's been stretched, then I'm going to put my mass here on the end, right here. Somewhere we'll say over here, okay, somewhere over here would be the equilibrium position. And that's where I'm going to take in place the center of my coordinate system. Right there is on equilibrium. Why? Because that's traditionally for springs where x is equal to 0, because that's the restored point of balance where a spring does no work on you or exerts no force. So this is 0 right here. All right. So this is the y-axis. This is the x-axis. So everything here is happening along the y-axis. Not only that, primarily along the negative y-axis. Now, so what's happened here is the spring has displaced us, has been displaced by gravity, and it's relaxed, so it's hanging in equilibrium. Okay, so that means that here you have gravity pulling down, but you also have the spring trying to pull it back to the equilibrium position, and they're balancing each other out. Okay, so I'm going to call this position right here y sub a. Now, for part B, what we do is we pull the mass an additional 30 centimeters down and then release it from rest. So once we find out what this position is, we pull it down 30 centimeters. We'll say down to here. I'll call this position y sub b. And then we release it from here from being at rest. So what's going to happen is the spring here has been stretched tremendously. So it's going to rocket this thing up. But as it rockets up, you also have gravity pulling down on it like this, trying to slow it down. Okay? So gravity is pulling down like that. Actually, let me fix that. This bothers me a little bit. Okay, that's better. So there's gravity pulling it down, and then there's the spring trying to restore it like that, right? Now, so we're going to need to find y sub a to figure out the total displacement from equilibrium that y sub b is, because this distance right here, this is 30 centimeters. Right? So once we find that distance and we add this additional distance, the distance that the spring was pulled down due to just the weight or the mass rather hanging stationary, then we'll have the total distance that the spring is going to be working on the mass to bring it back to equilibrium. All right. So really, what we have is a two-part problem here, and let's not forget that this is the ceiling. This is not x is equal to 0. All right. Or rather, y is equal to 0. So for part A, let's just quickly redraw our problem. Actually, I'm not even going to do that, I don't think. I think I'm going to be smart about this, and I'm going to go snag. So here's part A, right there. Let me clean it up a little bit so we know what we got. This nonsense right here doesn't matter. We'll redraw that. Okay. So for this part right here, we have, again, gravity pulling down, and we have the spring force here pulling back. Okay. Now, the thing is, though, is that this position, it's stationary. So right here, it's stationary. What that means is that if I were to draw a force diagram, which I'm going to do, I have the force of the spring acting up. I have the weight acting down. And they balance each other out. Okay, so I'll sum up the forces here to get the net force, of which I have two forces, a spring force and a weight, and they're going to cancel each other out. They're going to add up to 0. Okay, so what this does is to give me a relationship between the spring force and the weight that I can use to find out this displaced distance. Why is that? Well, that's because we know the spring force itself has a form that looks like this, minus k delta r. Okay, now, so here, remember, the negative sign just reminds us that this is a restoring force. And by restoring force, I mean it tries to bring you back to the spring's relaxed equilibrium position. Okay? So in practice, you put the sign in based off of your picture. Now here, delta r is going to be delta y because we're working along the y-axis. All right? So were I to look at my forces here, my spring force here is going to look like k times delta y. All right. So in the x direction, there's nothing interesting going on. In the y direction, there sure is something interesting going on. We have our positive spring force. We have a weight that's negative, and they balance each other out. So sort of following this mode of operation, I have k times delta y minus, now Fg is your weight, that's just m times g, and that's equal to 0. Okay? Now, so delta y would be this right here, this displaced distance, okay? Noting that this would be considered the initial position, and this position right here, which we had called y sub a, would be your final position. So if you wanted to write out givens for this, we have a mass that's 0.330 kilograms. We have a spring constant that's 25.0 newtons per meter. Our initial position for this is 0. Okay, and we're trying to find the stretched position, which is, I don't know why I'm calling it x here. That's habit because we do this thing along x so much, right? Sorry about that. And so we want to try to find y sub a. All right. So, and that's pretty easy to do because we know delta y here is just, y minus y naught. If you think of it like that, final minus initial. And y is just y sub a. Y naught is 0. So here, if you solve for y sub a, you get mg over k. All right. Now the mass here is 0.330 kilograms. G is 9.8 meters per second squared. And K is 25.0 newtons per meter. So if I do this, see 0.330 times 9.8 divided by 25. I get 0.129 meters. All right, so that's my y sub a. What's the relaxed position of the spring? 0.129 meters. Now, like I said, we're going to need this. Whoops, how did that happen? We're going to need this for part B. Why did I do that? It's 5:55 in the morning. Sleep is for the weak. All right, so this is part A, right? So now let's talk about part B. Part B has us pulling this thing down 30 centimeters and releasing it from rest. Now, thankfully, we now know what this distance right here is. Y sub A is, from a distance standpoint, 0.129 meters. Now, this is 30 centimeters, and 30 centimeters, remember, is 0.300, 00 meters. Okay, so our y sub b position really is going to be the sum of these, but look, it's down the minus y axis. It's in the minus y direction. Okay, so for part B, I'm just going to snipe this again. I really do like this little app. It's pretty cool. Pretty cool, man. Pretty cool. Go. So here's our new one right here. Now that we know this distance, let's start writing out our givens, okay? So what are we given? Well, as before, our mass hasn't changed. The mass is 0.330 kilograms. The spring constant is 25.0 newtons per meter. Okay. Now, our initial position is way down here where YB is. Our initial position is where YB is. And YB is going to be minus 0.129 meters plus a minus 0.300 meters. Remember, it's in the negative y direction. Okay, so when you add these two together, you get minus 0.429 meters. This is going to be its initial position, okay? We also know its initial velocity at that point is 0 because it's being released from rest, okay? Now, that's, okay. Also, final position for y is 0. That's where it crosses the equilibrium position. Now, what are we trying to find here? We want to find v. V when it crosses the equilibrium position right there. So how do we do this? Well, like I said earlier, the elegant thing about dealing with work is the fact that you literally just sum the works up to find the total work, each work representing the work done by one specific force. So here we have gravity, but we also have the spring force. So let's just talk about initially the action of gravity, okay? So if you think about just a simplistic picture, so we can understand what's going on with gravity here. We release this thing from rest, and it's going to travel upwards like this in a positive dy direction. But gravity is acting this way, trying to slow it down, right? So for gravity, your dr or your delta r, because gravity is a constant force close to the ground, is in the positive y direction. But the weight here is down, okay? So it would be, m times g in the minus y hat direction. Here, this is going to be, delta y hat would be delta r. So if I wanted to find, for example, the work due to gravity for this type of problem, it would simply be, because this is a constant force, F dot delta R. But F is gravity in this case, which is mg in the minus y hat direction. And delta R is up, like that. So it's minus mg delta y once you do the dot product. So this right here is the form for work for gravity. Noting the fact that our initial position, again, is, where yb is down here, and our final position is up at 0. Okay. Now, we also know from a spring standpoint, which I'll put here, the spring is trying to accelerate it up. It's trying to cause it to go faster and faster and faster up. So it's going to be doing positive work. And we already know what the form of, we'll call the spring work. This is the gravitational work. Okay, we already know what it looks like because we derived it. Minus 1/2 k times y squared minus y naught squared. Okay, now y naught here is our initial position. This is going to be, remember, y sub b. And this right here is going to be 0. Just like over here, if I were to take my work here and expand it out, this right here is y sub b. And this right here is, sorry about that. No, it's not. This right here is y sub b. And this right here is 0. Okay, so what that means here is that the work due to gravity in this case is going to be mg y sub b. Now, so it looks positive, but it's not, because look at what y sub b is. It's negative. So this is negative work. Okay. Here, though, if you look at it, you have a negative times a negative is a positive. Okay. So even though the displacement, or your y position here is negative, you square it, it becomes positive. So you do positive work. So as you can see, we're getting what we expect. The work done by gravity here is going to be negative, and the spring work is going to be positive. So the total work done here, okay, is going to be what gravity does plus what the spring does. And this is what's going to be responsible for causing the change in kinetic energy. So this is your work energy statement right here. Now remember, change in kinetic energy is, final minus initial. And we know this thing starts from rest. As the worst Bob Marley song ever says, no motion, no energy. For those of you that don't get that reference, I'm sorry. Okay. So what happens is basically this work simply goes into making this thing move from rest. All right. So what does this look like? So let's go ahead and just add these things up. I have mgy sub b plus 1/2 k y sub b squared, and that's equal to the kinetic energy looks like 1/2 mv squared, and this is what we're looking for. Okay, so let's flip sides and do a little bit of rearranging. If I multiply 2 through, I have, and divide by m, I have a k over m y sub b squared plus 2gy sub b. Now, if I take the square root of both sides, this is going to give us v, which is our speed. And I'm going to represent again the square root just because of all the stuff here as raised to the 1/2 power. Okay, so this is what we have to calculate right here. And let's just go ahead and plug the numbers in. There's my numbers right there. So V is equal to K, which is 25.0 newtons per meter over 0.330 kilograms times Y sub B. Y sub B is minus 0.429 meters, but it's squared, so that's going to make it positive. Plus 2 times 9.8 meters per second squared times Y sub B again, which is minus 0.429 meters. And that's what we have to calculate. Okay. So if you do it, let me do it real quick. It's the square root of 25 divided by 0.33 times, this is 429 squared times 9.8, 29. I get 2.35 meters per second. So there's your speed right there. So if I go up here, actually, let me just do it this way. What was that? That was 2.35. So it's pretty elegant, if you think about it. We didn't have to draw complicated force diagrams. We just had to make arguments from a standpoint of energy. And like I said, the nice approach here with respect to energy is that literally you just add the energies up. Okay. Now there are some caveats that you need to be aware of with respect to all this, and to sort of highlight them, I'll put them on a separate page here. So energy caveats. So things that you need to be aware of. The first thing is this: you only get a number. What that means is that the V that we got here has no directional aspect to it. Okay, you have to use your understanding of the problem to put in direction. The second caveat is that you'll notice if you go back and you look at the previous lecture and you review the lecture up to today, um, time isn't an issue. Now, there's a reason why we're not considering time right now. We're actually about to consider time through something called power. But the reason why is because all of the forces that we've talked about so far do not have a time dependence. So, for example, that was good coffee. So, for example, here, um, if you look at the spring force, even though we know the position of the mass attached to the spring changes over time, okay, the form of the force itself only depends upon how far you stretch it from equilibrium. It's only depends upon position. The same thing goes for gravity. Gravity is a constant. All the forces that we've dealt with up to this point have no time dependence. There's a reason for that. The fundamental forces that we see in nature in general have no time dependence. They only depend upon distances between things, which is a good thing. That means that we can apply all of our energy stuff so far with no issues. But if there's a time dependence in your force, you're better off actually going back and just taking the original approach, which is to do kinematics, which is number 3. Um, so if you only have a hammer, everything looks like a nail. Now, you may or may not have heard this before, but what this says is that if you have a limited number of tools, you're kind of restricted to use them. And many people take energy as a hammer. They're like, oh, I can solve anything using energy, and they immediately jump to the energy approach. Now, that's not necessarily always a bad thing because you can solve a lot of problems very simply using energy. We're going to see that in the next chapter when we talk about conservation principles. However, sometimes you can very quickly pound out your answer using kinematics, using, finding the equations of motion and just running with it. You could do that faster than you can setting it up and thinking deeply about where the energy's at. So, so I guess what I'm saying is that, at this point, if you think about what we have here with respect to energy, we can use the work energy theorem, for example, to solve kinematic problems with no issues. We just found velocity. We can find positions. Okay. But that doesn't mean that it's the easiest approach. So you have two competing methods by which you can find an answer, and one might be easier than the other, but they'll both give you the same answer. Okay, so it's internally consistent. So just be aware of that. All right. Now, so that said, let's talk about our last energy concept in this chapter, and that's power. Now, power is where we act to sort of bring time into the equation, if you will. And there are two types, and this is a definition, kind of like how work is defined. So there are two types. There's average power, and there's instantaneous power. Kind of like, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. And they're defined the following way. So here's the average one. So average power is the work that's done over time. Now, if you look at the units here, we know work has units of joules, Time has units of seconds. And this combination of units is called the watt. And you ready for it? It's abbreviated W. Yeah, I know. We've already used W here. Sorry, you're just going to have to deal with it. That's what it is. So these are watts. So now if you think about it, for example, if you have a light bulb that's a 100-watt light bulb, what that means is that light bulb presumably puts out, or uses actually, 100 joules of energy every second. So that's what watts mean. Okay, it's how much energy is being used or is going into whatever it is that's going on every second. All right. Now, instantaneous power looks like this. You just promote the different the changes into to differentials. Now, so this tells you how much power is being generated or being used at any given time. You can actually extend this one a little bit further if you use the differential form of work. The differential form of work we know is F dot dr. And I can suck the dr over dt up together, and this is F dot v. So you have two ways that you can write instantaneous power. So again, this is average, and this is instantaneous. Okay. Now, again, units in both cases, the watt, and this is it. Okay. So what I'd like to do is to work a real quick example. We're going to do a few more of these. So here's one. The sun puts out 3.828 times 10 to the 26 watts continuously. How much energy is emitted by the sun in a day? So in this case, we are given the power. It's 3.828 times 10 to the 26 watts. We are given the amount of time. Okay. It is a day. Now, if you convert the day to seconds, which is what we work in, that would be 24 hours in a day times 3,600 seconds in an hour. That's 86,400 seconds. And we would like to find the work. So this is really an average power problem. Okay. So it's as easy as this. So the power is 3.828 times 10 to the 26 watts times 86,400 seconds. So let's see here, 3.828 times 10 to the 26 watts. I get about 3.31 times 10 to the 31st. That is a tremendous amount of energy. Okay. To put that into perspective, if you were to express this in terms of megatons, and let me do calculation here real quick. This is ridiculous. It ends up being somewhere around 7.9 times 10 to the, let's see, 3, 6, 9, 10, 11, 12, 13th megatons. Wow. That's a lot. Okay. That's the issue. When you get to numbers like this, there's just no reference that you can use that makes any intuitive sense. Okay. Now, here's another example. 1 horsepower is defined as the work required to lift 550 pounds a distance of 1 foot in 1 second against gravity at a constant velocity. What is this in watts? Okay, now, so let's draw a picture here. Here's the ground. Here is your mass. It has a weight in the imperial system of 550 pounds. Now, we can convert that weight from the imperial system to the metric system, or we can just express it in kilograms and convert it that way. That's how I'm going to do it. Now, typically, you have some sort of contraption that you see at least used in reference to drawing this, of like a pulley, and then there's like a horse. I suck at drawing horses, so here's a horse. That's a horse. Okay. Apparently he's levitating. And so, attached to the horse, to one side of the pulley, coming down the other side of the pulley is your rope. So what happens is the horse goes this way at a constant rate. The mass here is lifted in turn at a constant rate. You have a tension in the rope that goes up like this. You have the weight going down like this. And if it's being lifted at a constant velocity, what that means, as per Newton's first law and as per Newton's second law, is that the sum of the forces is equal to 0. If it were accelerating, remember, it would be non-zero. So in that case, it's 0. So if you're just to think about a simple force diagram here, where you have the tension up, you have the weight down, like this. When you sum up the forces to get the net force, you're going to get 0. So what that means is that if you look in the x direction, there's nothing interesting happening. In the y direction, the tension, which is the thing that's doing the work here, okay, through the horse, is going to equal to the weight at the end of the day. So this is the thing doing the work, but it's doing positive work in this case. Because if you take a look here, this right here is the direction of dr, or delta r, and this right here is also the direction of the tension. Okay, so it's lifting. Now, so here we're given that our weight is 550 pounds. Now, what I'm going to do is to convert that. Give me a second here to get my conversion stuff here. I know, just from a conversion standpoint, and this is going to be convenient because all this is imperial. Horsepower is an imperial unit, but it's used, so frequently. 1 kilogram on the Earth weighs 2.205 pounds. I also know that 1 foot, which is how far we're lifting this thing in 1 second, is 0.3048 meters. Okay, so thankfully we know the displacement over which we are lifting this. We're lifting at 0.3048 meters. Okay. And if you were to convert this to mass, when you convert it to mass, you get, let's go ahead and do it here real quick. Uh, 2.205. This is about 249 kilograms. Okay, so, and we also know the elapsed time. We're lifting it for 1 second. What are we trying to find? Well, we'd like to find the power, but we want to express this, like I said, this is what a horsepower is. So remember, power, at least average power in this case, is your change in work over change in time. And here the change in work is just the work. Really, it's better written as work over change in time. Okay, so the work here, since this is a constant force, is F dot delta R over delta T. The force that's doing the work here is the tension. We're lifting it over a distance of delta Y. They're parallel to each other, so the dot product is plus 1, it's positive, over delta T. And the tension has the form of M times G. Okay, so if you plug the stuff in here, you end up with, let's see here, 249 kilograms, 9.8 meters per second squared, 0.3048 meters in 1 second. And if you do the math here, you get 245, or not 200, but 745 rather. 745 watts. So there's a conversion between horsepower and watts. 1 horsepower is the same thing as 745 watts. Now, what's cool about this is that since people who brag about what horsepower their car is, like big numbers, you could get like one of those little itty bitty, what do they call them? The minis or whatever. Not a mini. What's that little eco car that like a strong wind would blow over? That has like 2 horsepower. But the thing is that if it had 2 horsepower, it would have something like, almost 1,500 watts. Well, that's a lot. So you could brag about how many watts your engine is. And it's a joke. Come on, go with me, man. It's like 6:30 in the morning. But nobody here to amuse but myself. Okay, so that said, pretty good example. All right. Now, here we're going to do another one. Okay, so in this problem, we're asked how many watts of power does a car's engine need to accelerate a car from 0 to 60 miles per hour in 4.2 seconds. The car has a mass of 1,200 kilograms. So the first thing we're going to do is to draw a picture. Let's draw us a little coordinate system here. Here's the y-axis, here's the x-axis, here's our car. We'll have our car accelerate to the right. Its initial position is going to be 0. Somewhere over here, we're going to have to calculate x potentially, maybe not, you'll see. Over here, the car has accelerated to a final velocity in the x direction of 60 miles per hour. Now, obviously, we're going to have to convert this to meters per second. Initially, though, the car's initial velocity is 0. Now, we also know that the car has a mass of 1,200 kilograms. It takes 4.2 seconds for the car to get from here to here. Now, so we're being asked for watts, which obviously is power. So let's just go ahead and write out our givens. Initial velocity in the x direction of 0. Final velocity is 60 miles per hour. Let's go ahead and convert that. If you follow your standard conversion here, let's see. 60 miles per hour ends up being around 26.8, we'll say, meters per second. Okay? Now, it takes us 4.2 seconds to get from here to there. And we have the mass of our car, which is 1,200 kilograms. We're trying to find the power. All right? So we know the force is going to be this way, right? This is going to be the direction of our force. We also know that this is going to be the direction of the displacement. So we have a couple of different options here that we can use to find the answer. I'm going to choose our conventional definition of this right here. Okay. Now, the reason why is because this is starting here and ending here, so we're being asked for total power. So that would be the average between here and there, basically. So let's talk about what the work is here. Well, as you can probably imagine, our acceleration here is going to be constant, right? So, excuse me. The work here that's being done from here to here is going to be, again, F dot delta R. All right. The elapsed time we already have, that's 4.2 seconds. So we're going to need to calculate our displacement, and we're also going to need to calculate our acceleration. So here, if you write down your kinematic equations for constant accelerations, you have v sub x is equal to v naught x plus ax times t. You have x is equal to x naught plus 1/2 ax t squared plus v naught x times t. And you also have vx squared minus v naught x squared is equal to 2 times a sub x times x minus x naught. Okay, so what I propose we do is to use this to find the acceleration, and then use this right here to find what the displacement is going to be, which is what this is right here. Then we can put it in here, because from here we can already see that delta R is really just going to be delta x, x hat. So we need delta x, which is what this is right here. Okay, so really you can rewrite this as 2 times a sub x times delta x if you want. Now, we also know the forces in this direction, and thankfully these guys are parallel to each other, so we can write our forces, f sub x, x hat if we wanted, like we've done in the past. And, our dot product is going to look basically just like f sub x times delta x. So we already know what that's going to be. So, here you can put that in just to get prepped for it, which looks like that. Okay. So, like I said, we have a couple different options. We could calculate the average velocity, that's delta x over delta t between these 2 points, and then plug it in here, find the force. I mean, basically, you end up having to do the same amount of work in both situations. Work, yes. Now, anyway, so let's just go ahead and find the acceleration. Like I said, I'm going to use this right here. We're going to note the fact that v naught x is 0, so that's 0, that's 0, that's 0 as well. So our acceleration in the x direction is just going to be v sub x divided by t. And V sub x is 26.8 meters per second. T is 4.2 seconds. And if you do the math here, let's see, 26.8 divided by 4.2, you get 6.38 about. So this is about 6.38 meters per second squared. Okay. Now, so that means that we can use this right here to calculate the force, because we know the force here has the form of just m times a sub x. I mean, that's what the force is going to be. All right. So so it just goes there. So now let's go ahead and use this right here to find what our displacement is going to be. And if we do that, our displacement is going to equal to Vx squared over 2 times a sub x. Okay. So Vx squared, that's 26.8 meters per second. You got to square that, divided by 2 times 6.38 meters per second squared. Okay, so our displacement here is going to be let's see, 26.8 squared divided by 2 times 6.38. So you end up with something like 56.28 meters. Okay. Now, but I'd like to show you something here. Okay, now watch this. So instead of putting the numbers in here, I'm going to take and plug this into this. Okay. So my average power would be m times a sub x times delta x. Now delta x is v sub x squared divided by 2 times a sub x. Over that. Oh, look at this. Huh. And in fact, this looks suspiciously familiar on the top. It looks like 1/2 m v sub x squared. Like I said, there are a couple different ways to do this. Now, why would there be kinetic energy up at the top? Well, I have a question for you. Will you agree with me here that when I do work, I'm causing a change in kinetic energy? Well, I hope so. I mean, that's kind of been the whole point of this entire lecture, right? And if your initial velocity is 0, then all of the work that you're doing from here to here goes into motion. So writing your power this way works, but you could also have written it this way as well. Okay? So you can see how elegant energy can be. So let's use this form. 1/2, 1,200 kilograms. V, again, is 26.8 meters per second. You have to square that. Divided by 4.2 seconds. Oh, need a second here. Times 1,200 times 26.8 squared divided by 4.2. And I get something like 1.03 times 10 to the 5th joules. Now, in a situation like this, using kilo is probably what we would want to do. So this would be something like 102 kilowatts. Sorry, that's not a joule. I apologize for that. So watt. Okay. Now you could even go so far as to express this in horsepower. Like what horsepower does this car have, basically? And if I were to go over here and look at the fact that it takes 745 watts to produce 1 horsepower, if I divided this by 745, I get about 138 horsepower. Okay, which is not much at all. Okay, um, so that about wraps it up for our discussion about kinetic energy and work and how all these things interplay. You know, let's not forget that when you're dealing with energy, you get a number. If you ask, what's the velocity, you're not really getting a velocity; you're getting a speed. You know, um, so you have to be careful about that. Although let's not forget that work, has the positive and the negative aspect of work means something. Likewise, we generally don't consider time. With the exception of power, which is where you introduce time into energy. That's it. Okay. Finally, you got to avoid the hammer approach. Okay. There are going to be times in which energy is useful, and there are going to be times in which it's probably better just to take and do simple kinematics to get your answer. Either one will give you the correct answer, but it's all about avoiding extra work. But some people prefer the extra work, and that's okay. All right. So that's it, and I'll see you next time.